So in this video, we're going to be looking at the equilibrium expression. We're going to look at Kc and Kp and the factors that actually affect it as well. Now, in terms of this, we know that concentration, temperature, and pressure, they're the only three factors that will actually affect our position of our equilibrium. In terms of Le Chatelier's principle, we know, of course, it shifts either to the left-hand side or towards the right-hand side. The thing is, in terms of adding a catalyst, we know that has no effect on the position of our equilibrium. It only increases the rate of reaction. Now, if we were to look at Kc and Kp, here it's going to be slightly different, because if we were to look at concentration and pressure, initially the value of Kc and Kp, the ratio of our products to reactants, regardless of what we're actually dealing with, of course I'm just talking about it generally here in terms of the equilibrium constant, initially that will actually change, and we need to be aware of that initial change. And then what's going to happen is our equilibrium will shift, and then that change is going to be minimized, so Kc and Kp, they actually return back to their original values. So overall, changing concentration, pressure, adding a catalyst, none of these actually affect the value of Kc or Kp. Now, if I were to look at temperature, however, temperature is actually the only factor that affects Kc and Kp permanently. If it shifts once, it will shift that way only, it won't shift back. The value of Kc and Kp is only affected by temperature. Now you can see here I've got a generic Kc expression where I've got the concentration of products over reactants. I've got the top term, which is what we can call this over here for our products, divided by our bottom term, which is going to be our reactants, or the numerator and the denominator. Now in terms of Kc, what does Kc actually mean? Well, Kc, if it was, let's say, something like 1, we know we've got an equal amount in terms of products to reactants. That ratio, our concentrations are pretty much equal. But then the thing is, let's say if I were to have a greater concentration of my products to reactants, let's say if I've got more products than reactants, let's say if that top term is going to be larger than that bottom term, let's say if Kc was going to be in a ratio where we ended up with 100 to 1 instead of course 1 to 1, well, we would end up with a very large number if we were to calculate that, and we end up with a number that's going to be 100, and that means, of course, I've got more products compared to my reactants. That number is going to be larger. We know, of course, the concentration of our products is greater than our reactants. Our top term is going to be larger. Our equilibrium is going to be shifted towards the right. So what we can say is that if the concentration of our products is going to increase, then Kc in itself, that's going to increase as well. Now, what about if you were to flip this scenario where Kc was going to be equal to, let's say, 1 divided by 100, where the concentration of our reactants is going to be greater? Well, we would end up with a very small number in this case that's going to be below 1. We end up with something like 0.01 in this case, where you can see it's a very small number. We know our equilibrium is shifted to the left hand side. It's shifted more towards the reactants. That bottom term is going to be much larger compared to that top term. Now, what can we actually make from this then? If our concentration of our reactants is greater than our products, well, if the concentration of our reactants, if that were to, let's say, increase, then our Kc value, that's going to get smaller, that's going to decrease. So the smaller the Kc value, the more towards the reactants it is. The greater the Kc value, the more towards the products it's going to be. Now, why is this going to be important? Well, we need to be able to explain to the examiner why changing concentration, pressure, and adding a catalyst don't actually affect the value of Kc and Kp permanently, but only do so initially. And then, of course, why does temperature affect Kc and Kp permanently? So yeah, if we were to look at our first example, if I'm changing the concentrations, let's say if I'm looking at this equilibrium here, I'm dealing with N2O4, that's forming 2 lots of NO2. We're asked to explain what would happen to the value of Kc if N2O4 was added to the following equilibrium. Now, we've got to think about it like this. First of all, in terms of a fraction, I'm dealing with N2O4. That's going to be, of course, my reactant. If I were to increase this bottom term over here, we know that Kc is going to, of course, decrease. Why? Because we're going to be dividing by a bigger number. We're going to be dividing by a bigger reactant in this case. If we're dividing by a bigger reactant, that Kc is going to get smaller. But the key wording is it's going to get smaller initially. Now, let's say if I were to add N2O4 in terms of Le Chatelier's principle, you can see that's, of course, going to be a reactant. If I were to increase the concentration of my reactant, I know my equilibrium is going to shift to the right to oppose that change in concentration. And so I know this NO2, that's going to increase. If I were to look back at my fraction, that's my top term there, that's going to increase. That's going to increase back up until Kc returns to its original value. Because remember what we said, that top term, if that increases, Kc is going to increase as well. Now here's what we need to be able to say in terms of the exam. The bottom term in the Kc expression initially increases and Kc decreases. The equilibrium shifts to the right hand side. The top term in the Kc expression increases until Kc returns back to its original value, and we give the final statement, which is Kc and Kp, they do not change with changes in concentration. Now normally this type of question is worth about 2 to 3 marks, but of course I've gone about it in 4 points that you always mention. First of all, what's the initial change? Which way does the equilibrium shift and why? And then of course, how does it return back to its original value? And the overall statement that we give every time, that Kc and Kp, they don't change with changes in concentration. Moving on, what about if we were to look at another example where we're dealing with pressure? Pressure, we normally deal with that in terms of Kp, of course. We know Kp over here in terms of this equation, it would look the same, but we've got P, small p, circular brackets as well. If I were to increase pressure in this case, overall of the system, think about it, the total pressure, if that increases, all of the partial pressures is going to increase as well. Because remember, the molar fraction staying the same, but of course, if our overall pressure increases, the partial pressures, they're going to increase. Now, let's say if I were to double pressure in this case, what would happen is that top term there, that's going to, of course, times by 2, but it's going to be times by 2 squared because we're dealing with 2 moles of gas. That bottom term is going to be times by 2 as well, but it's going to be times by 2 to the power of 1 because, of course, you can see we've got 1 mole of that gas. If we were to look at this, right, we're times in both of them by 2, so both of our top term and our bottom term, that's going to be, of course, doubling, but because that top term is going to be 2 squared, technically it's going to be times in by 4 at the top and times in by 2 at the bottom. So what we can say is that top term is going to increase more. Now the thing is, if that top term is going to increase more, we know that the product increases, Kp initially is going to increase itself. But if we were to look at this in terms of Le Chatelier's principle, so again we need to think about which way the equilibrium will shift. I've got 2 moles of gas on the right hand side, 1 mole of gas on the left hand side. I know my equilibrium will shift to the side with the least moles of gas if I increase pressure, so I know it shifts to the left hand side. That means that, of course, N2O4, that's partial pressure is going to increase. We know, of course, how equilibrium shifts to the left. We end up with more N2O4 being produced, and of course the concentration increases and the pressure actually increases, the partial pressure increases of N2O4. So of course, if our reactance is increasing, that bottom term increases, we know, of course, Kp will return back to its original value, because if that bottom term increases, we know Kp is going to get smaller. Initially it went bigger, and then of course afterwards it returned back to its original value because that bottom term increased. So yeah, what would I need to be able to say in terms of the exam to get the marks? The top term in the Kp expression doesn't just increase, it increases more, and so initially Kp increases, the equilibrium shifts to the left hand side, the side with the least moles of gas, and then the bottom term in the Kp expression, that's going to increase until Kp returns back to its original value. Kc and Kp, they don't change with changes in pressure, and that's how we answer our pressure questions. Moving on then, what about if we're dealing with temperature? Now in this question, we're asked to explain the effect of an increase in temperature on the value of Kc. Well, here it's going to be a bit more different because we've got to think about that change being permanent. It does actually affect the value of Kp and Kc, whereas concentration and pressure, we've seen they don't. I'll look at it, the forward reaction, that's going to be, of course, exothermic. I know the reverse reaction, that's going to be endothermic. So in terms of this then, I know an increase in temperature, because that's what we've got over here, is going to shift it in the endothermic direction. So I know it shifts to the left hand side. Products, that's going to decrease. The reactants, though, that's going to increase. So overall what's happening is that bottom term, that's going to be larger than, of course, our top term. Now we know if that bottom term is going to be larger, Kc is going to decrease. But how would we actually word this in the exam? Well, this one's going to be a lot simpler. Here's what we need to say. The equilibrium will shift left in the endothermic direction. The bottom term in the Kc expression increases, and then Kc decreases. And overall, the effect that we can actually see is Kc actually decreases. So yeah, that summarizes the changes in temperature and how that affects the values of Kp and Kc. Now moving on, what about if you were to try a task? Feel free to pause the video, use everything that you've learned to answer this question. Pause the video, resume once you're ready to go over the answers, and we'll go over it together. So looking at this question then, right, we need to be able to think about this in terms of Le Chatelier's principle. We've got an equilibrium here. We can see the forward reaction, that's going to be, of course, the endothermic reaction. The reverse reaction, that's going to be the exothermic reaction. In terms of our moles of gas, we've got a 1 to 1.5 ratio. So of course on the left hand side it's 1, on the right hand side it's going to be 1.5. Of course we need to focus on gases. Any solids, liquids that you see, you normally tend to get rid of them and focus on the gases. Now starting off, in terms of the rate of reaction, we need to decide, does that increase, decrease, or is it going to stay the same? If we use a catalyst, we know the rate of reaction, that's going to increase. We end up with more particles with energy above the activation energy. We end up with more successful collisions. Increasing the overall pressure, we know, of course, we end up with more concentration of molecules. We end up with, of course, more particles per unit volume, more frequent collisions, and so more successful collisions as well. So, of course, the rate of reaction increases. If I were to decrease the volume of the reaction container, it does the same thing as increasing pressure. So, of course, that's going to increase as well. If we were to look at decreasing the temperature of the reaction, if I decrease the temperature, the rate of reaction is actually going to decrease because we end up with less particles with energy above the activation energy. We end up with less frequent collisions, and so we end up with less successful collisions overall. The rate of reaction decreases. Now, what about if I were to look at the last one, increasing the temperature of the reaction? Well, here we know, of course, that's the opposite of the top one. We've got, of course, more molecules with energy above the activation energy. We know that we end up with more frequent collisions, more successful collisions, so we know it's going to increase as well. So moving on then, what about if we were to look at equilibrium yield in this case? Of course, if we're dealing with SO2 gas in this case, which of course is going to be our product, we look at it, if I use a catalyst, that actually has no effect on the equilibrium yield. It only increases the rate at which equilibrium is established. The rate of reaction is what catalysts are involved in, not the yield. If I were to increase the overall pressure or decrease the volume of the actual reaction container, we know our equilibrium is going to shift from right to left. If I were to increase pressure, I know, of course, that it's going to shift in the side with the least moles of gas, which is going to be the left hand side in this case. So in that case, I would end up with our equilibrium yield of SO2. That's actually going to be decreasing for both of these cases. So it decreases here, and then I've got decreases over here as well. Now, what about the next one? If we're looking at decreasing the temperature of the reaction, well, we've already said the reverse reaction is going to be exothermic. So, of course, it shifts to the left. We end up actually reducing the amount of SO2 being produced. So in that case, that's going to decrease as well. The last one, increasing the temperature of the reaction, it's going to be the opposite, shifts towards the right, the endothermic actual reaction. So we know, of course, that's going to increase. What about Kp? Well, Kp is unaffected by using a catalyst and by changes in concentration and by changes in pressure as well. The only thing that affects the value of Kp and Kc is temperature. If the equilibrium, if I decrease the temperature, is shifting towards the left hand side, Kp, we know that's going to decrease because that bottom term is getting larger. Think about it like this, always draw this out. Kp is equal to P over R. Think about which way it's shifting towards the left hand side if you decrease temperature, and you know the left hand side is reactants. The bottom term in that fraction is going to get larger, so Kp is of course going to get smaller. So we know, of course, this is going to be decreases. Look at the last one. What about if I increase temperature? Well, in this case, it's going to shift to the right hand side. We make more SO2 and O2. Our products this time is going to increase. That top term gets larger. We know Kp overall, that's going to, of course, increase. So, of course, Kp is going to be increasing.